All right, this is part 2 of lesson 4.1, and I'm going to go through these kind of fast because, again, most of them are review. So again, I like when we just have generic functions and values because, again, the AP test is going to ask you a lot of these. So here, h of x is the product of f and g, and we want to find the derivative. So we're going to use the product rule. So remember, to find the derivative of a product, it is the first times the derivative of the second plus the second times the derivative of the first. And if you want to, you can just leave in all those x's. So it's f of x times g prime of x plus g of x times f prime of x. And then we just went to plug in 4. So h prime of 4 would, plugging in 4s wherever there's an x, f of 4 times g prime of 4 plus g of 4 times f prime of 4. And they told us all of these values. F of 4 is 2. G prime of 4 is 5. G of 4 is 3. And f prime of 4 is -1. And so that's going to be 10 minus 3, which is 7. All right. So really easy to do if you know all of your rules. Here we have j of x, and we want to find j prime of 4. So j of x is this f function being cubed. So what I have is a nested function here, a composition really. I think this really needs a chain rule. So for j prime of x, we're going to take our power and drop it down. So 3 squared. And then we have to take and multiply by the derivative of the inside. So f prime of x. And I think that's it. So let's see what we've got here. So j prime of plugging in 4s everywhere. That'd be f of 4 quantity squared, times f prime of 4. All right, so we have 3. And then f of 4 is 2 being squared times f prime of 4, which is -1. So 2 squared is 4 times 3 is 12 times -1 gives me -12. Okay. All right. Here we have k of x. And again, it's a composition of two functions. We have an outer function times an inner function. And again, we want to find the derivative. So again, this is the chain rule once again. So to find k prime of x, it's going to be the derivative of outside times the derivative of the inside. So f prime of g of x times the derivative of the inside, which would be g prime of x. So I'm going to go ahead and plug in my 4s everywhere. So we have g of 4 times g prime of 4. All right, so this looks complicated, but we just need to work the inside first. G of 4 is 3. And so now we have, it's telling us to do f prime at 3. We can't do that. Oh, that's interesting. I don't have f prime at 3. Oh, poop. All right, times g prime at 4, which we do know. I'm just going to leave it like this. Obviously, this is a mistake on my part, or wherever I got this from. I wonder where I got that from. Oh, I have it here. I don't know. Let me look here. They have an answer. Hold on. Okay, so I see what I skipped here. There was one thing left off in my instructions here. It did say f prime of 3 equals -2. I don't know how I missed typing that in, but I did. And there it is. Okay, well, that helps very much. So f prime of 3 equals -2. And then g prime of 4 equals 5. And negative 2 times 5 is negative 10. There we go. Much better. Okay, so funny. Wow. Sorry about that. All right, let's do some more here. Okay. We haven't done one of these in a while, but I think it's just really good to think about. And this one question really takes us through kind of a lot of things. So example 4, the position in centimeters of an object moving on a horizontal line is given by S of t equals yada, 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 with t measured in seconds. So again, this is some particle and it's moving on a horizontal line and it's sort of doing this crazy cubic pattern back and forth, kind of swooping back and forth. We want to determine the object's total distance traveled between 0 and 2 seconds. And there are kind of a lot of ways that you could do this. If you want to get a visual of what's happening, you can just start with 0 and maybe make a ST chart of, I don't know, 0 and 0.2 and 0.4 and 0.6 and 0.8 and see how that particle would be plotted on a horizontal line. So kind of interesting, but it moves to the right and then it moves to the left and then moves back to the right. We want to find the total distance it travels. And in order to figure that out, we need to know when it's turning around. We know that a cubic function has this sort of stretchy S shape, and we're just going to translate that back in a horizontal line. So it's moving to the right and to the left and to the right. Well, in order to make sure that we count all that movement to the right and to the left and to the right, we need to know when it's changing directions. And to do that, we want to look at the velocity. And because when the velocity is equal to 0, then we know when that particle has to stop so that it can turn and go the other direction. For just the briefest of moments, it has to pause and then to go the other way. So to find the velocity, we're going to take the derivative of this S of t function. That's going to give me 6t squared minus 6t minus 1. And we want to know when that's set equal to 0. I would normally try to double bubble, but this doesn't double bubble. So I'm going to use my calculator. And I'm going to graph 6x squared minus 6x minus 1. And I'm going to use 0. So I'm putting the left-hand side in y1 and the right-hand side in y2, just so I can calculate the intersection really easily. If you have a Casio, it's super easy to do it. You don't really need the equal to 0 part, but our TIs we do. Oh, I'm going to do a zoom standard. So you can see that it's just this little parabola, and we want to know these points of intersection right here, the zeros. And so I'm going to calculate the intersection number 5. I'm going to move Tinkerbell close to that intersection and do enter, 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 and I get t equals negative 0.145. And I'm going to do it again. Second, calculate the intersection. I'm going to move Tinkerbell over and do enter, enter, enter. And we get 1.145 for that second point. And the reason I like to draw the shape of this graph is you can see that our graph is positive to the left of negative 0.145, negative below the axis, and then positive to the right of 1.145. And that's important because that tells us that our particle was moving right for negative values of x. And then between here, it's moving to the left on our horizontal axis. So first he was moving to the right, and then he turns around at negative 0.145 seconds and moves to the left. And then again, he switches direction at 1.145 and moves back to the right. So that's what those positive above the axis and below the axis mean for this type of problem. So in order to know the total distance between 0 and 2 seconds, we have to know his actual position at these changes. So his position so we want to know S of 0. And do I want to find S of negative 0.145? No, we don't need that one because we only want it between 0 and 2 seconds, and that is not inside the interval. So I'm going to use S of 1.145 and his position at 2 seconds. So that's his position at 2 seconds. So let's figure out that. Again, I'm going to go back to my calculator because these numbers are ugly. And I'm going to type in the position equation. So 2x cubed minus 3x squared minus x plus 8. And of course, those x's are really t's. We've got this cubic sort of shape. I'm going to imagine it horizontally. There you go. All right, so let's see. I'm going to do trace 0 to see what the position was at 0, and we know it's 8. I'm going to go ahead and do 1.145, and I get 5.924 centimeters, and then at 2 seconds, he's at 10 centimeters. So what's happening here? Well, at 0 seconds, 0 is like right here. He is moving to the left, and so he's moving from 8 centimeters back to the left to 5.9 centimeters. So he's moving left. Let's see how far. So I'm just going to subtract 8 minus 5.924, and I get 2.076 centimeters. So he's moving at 0 seconds. He starts at 8, and then he moves to 5.924, so that he traveled a distance of 2+ centimeters. And then at 1.45, he switches, and now he's moving to the right. So here he's going to the right, and you can see he started at a position of 5.9, and he's moving right to this position at 10 centimeters. So again, we want to know that distance, 10 minus 5.924, and we get 4.076 centimeters. So his total distance is 2.076 centimeters plus 4.076 centimeters, which is 6.152 centimeters traveled between 0 and 2 seconds. Kind of interesting to think about. Okay. All right. We've got just a couple more here. Oh, last one. All right, I hope you can read it. I'm sorry, it's small. It says, let f be the function defined by f of x is 2x plus 3e to the negative 5x. And let g be a differentiable function with derivative given by g prime. Oh, they're giving me the derivative. That's interesting. All right. It is known that the limit as x approaches infinity of g of x is infinity. And we want to know what is the limit as x approaches infinity of f of x over g of x. So first of all, we would want to do direct substitution, right? That's our first step whenever we're evaluating the limit. So I would want to find the limit as x approaches infinity of f of x and the limit as x approaches infinity of g of x. Well, they told me the limit as x approaches g of x is infinity. So let's plug in our original function here and see if we plug in infinity. Well, let's see, that'd be infinity plus. Well, if we plug in infinity, that'd be e to the negative infinity. Well, that's 0. E to the negative infinity is 0. Yeah. All right, so that sort of goes away, but we still get infinity. So here we have, again, this indeterminate form, so we need to take the derivatives. So let's go ahead and find the derivative. The derivative of f of x. Well, the derivative of 2x is 2, and here we would have 3e to the negative 5x times, again, the derivative of the exponent, so that'd be times negative 5. And so to clean that up, we'd have 2 and then a minus 15, e to the negative 5x. And then the limit as x approaches infinity of g prime of x I'll just use 1. Weird. All right. G prime of x, they told us G prime of x, so I have that. It's 1 over x plus 4 cosine of 5 over x. All right, let's do some plugging in that infinity stuff. If I plug in infinity again here, e to the negative infinity is 0. So I'm just getting 2 for the numerator. And here, well, 1 over infinity, again, that approaches 0. If we take 1 and divide it an infinite number of times, that's like 0. Okay. And then here we have 5 over infinity. Well, that's like 0. So this is like 4 cosine of 0. Again, that approaches 0. All right, so cosine of 0 is 1. And so we have 2 over 4, which is 1/2. All right, that was really tricky. And I'm pretty sure that was not a calculator problem. This is something that you would not have been allowed to use your calculator on. All right, ladies and gentlemen, that does it for me. Have fun with a little bit of review and l'Hopital.